Alright, so let's discuss some strategies to answer the AP Physics 1 FRQ. So number 1, do not skip the information before the actual question. So let's say you're running low on time and you just started the question. You may be inclined to actually skip that first paragraph and jump straight into the question. However, I would strongly advise against that. And that's mainly because that first paragraph has some really key information and some key points that are not only consistent throughout the entire question, but may also help you answer that question. So if you don't read that part, then you might lose out on some really, really easy points. So try not to skip reading that part. All right. And the second one, in my opinion, the most important one, you should think about the physics principle, not the equation. Many students jump into physics questions and think about, okay, what equation can I use to solve this problem? However, that is not the best approach, and mainly because there are so many equations that you might get lost into finding which one you really need. So the best thing you should do to avoid that is to ask which physics principle is applicable to this situation. And not only will this allow you to minimize the amount of equations that you can use to solve the question or solve the problem, but it also allows you to analyze the situation from a more conceptual standpoint. Okay, and number 3 is to be brief when appropriate. The AP Physics 1 exam will ask you to briefly explain your reasoning. And whenever it asks you to briefly explain your reasoning, you have to be succinct and to the point. Many students like to write paragraph-length responses, which is not only completely unnecessary, but is a total waste of time. So whenever they ask you to briefly explain your reasoning, I would suggest 1 to 2 sentences at most. All right? And number 4, for deriving equation questions, only include variables that are given and simplify completely. So we will be looking at more. We will be looking more into these questions throughout the video. But for example, it will ask derive an equation or derive an expression for acceleration using variable 1, variable 2, variable 3, and physical constants as necessary. So whenever it gives you that list of variables, you should really just stick to that. It's kind of giving you a hint as to what your expression should include. So try not to include any extraneous information. And physical constants means basically like gravity or universal gravitational constants, those sort of constants. So yeah, and whenever I say simplify completely, I mean that if you can cancel stuff out, cancel it out. If you can combine like terms, combine like terms. If you can factor something out, definitely factor it out. Okay, and moving on to number 5, never draw free body diagrams never draw free body diagrams with components in the answer space. So there will be at least one question on the AP exam where they're going to ask you to draw a free body diagram about a center of mass or about an object, and whenever you're doing that, you should never ever include components in your free body diagram. You should only include the forces that are, you should only include the main forces that act on the object. If you do need to draw a free body diagram with components, which may be necessary, then you should just go on the side and quickly sketch it out, but do not draw it into the answer space, or otherwise you will get points off. Alright, so now that we've went over the various strategies, let's go ahead and apply them to an actual question. And this is from 2016, so let's take a look at it. Right off the bat, I can see this really cool diagram on top. It's a ramp with an angle theta and a wheel of mass m. And I can think of some physics principles that this question might be asking about. Namely, forces, definitely forces, dynamic forces, rotational motion probably might come out, and maybe energy, but I don't know, let's see. So the first thing I'm going to do is definitely go ahead and read that first paragraph up here. So it says, a wooden wheel of mass m consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. So some of this information might seem kind of obvious, but if we hadn't read it, then we may have assumed that the surface was frictionless. But in the top paragraph, it gives us some really key information that is consistent throughout the entire question, and that is that the fact that this wheel rolls without slipping, therefore it has some sort of friction. In this case, some force of static friction. So now that we've read that, let's go ahead and jump right into the question. Part A says, on the diagram below, draw and label forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The lengths of the arrows need not indicate the relative magnitudes of the forces. Okay, so that's a lot of information to take in, but let's go ahead and summarize what they're saying. So they're just saying that draw a force diagram for this, or a free body diagram for this scenario of this object. So usually you might in class have you might have drawn free body diagrams with a center of mass represented by a dot. So let's go ahead and draw a free body diagram like that. So you would have a force of normal pointing in that direction and a force of gravity pointing directly downward. And right up the ramp, you would have a force of static friction. Okay? So, yeah, in essence, this is a correct answer. However, they do say that we have to clearly indicate at which point on the wheel each force is exerted. So in order to do that, we can't just draw it from the center of mass like this, which is a common mistake people might do on this question if they haven't read it carefully enough. So having understood that we have to draw the force from the point at which the force is exerted, let's talk about the force of normal in that situation. The force of normal always starts from the surface and points perpendicularly upward onto the object. So in this case, it would start at the surface and point perpendicularly upward and through the center of mass of the wheel, indicating that the force of normal technically pushes up on the wheel. And now the force of gravity always starts from the center of mass and points downward. So assuming that the mass is evenly distributed throughout this object, I'm going to assume that the center of mass is the center of the wheel, and it's just going to go directly downward, like so. And finally, we have the force of static friction. So the force of friction always starts at the point of contact between the surface and the object and points in the direction opposite to its direction of motion. So in this case, we can logically say that this wheel has a direction of motion down the ramp, so therefore the force of static friction would be in the opposite direction, or up the ramp. And it starts at the point of contact between the surface and the object, so it looks something like this. And that is your force of static friction. All right, so this is a really easy question. You know, you're just drawing a free body diagram, which I hope you guys are aficionados at. But I think the tricky part of this question is not reading this completely. So make sure you read the question extremely thoroughly. All right, so let's move on to part 2. As the wheel rolls down the ramp, which force causes a change in angular velocity of the wheel with respect to its center of mass? Okay, so now we're talking about forces, but we're also talking about changes in angular velocity. So when I see anything angular, I'm immediately thinking of rotation. And whenever I think of rotation, I also think of torque, because when a wheel, for example, is applied a net torque, it also changes its angular velocity, right? That's just common sense. So let's go ahead and add a little bit of components, or add on the components to this free body diagram up here. So we have the FG in the y direction, and we have FG in the x direction, force of gravity in the x direction. So obviously the wheel is moving down this axis, right? So many of us might think that force of gravity is the one that is changing its angular velocity because it is pulling the wheel down the ramp. However, that is just a component of a force. It's not directly making it turn. Remember, torque is some force multiplied by a radius perpendicular to that force that causes it to rotate. So technically, the force of gravity in the x direction would point from the center of mass of the wheel. But is the center of mass causing it to rotate? Because the lever arm would then be 0, correct? Therefore, the torque would be 0. So what's actually causing it to rotate is the force of static friction, because it applies a net torque, therefore allowing the wheel to roll down the ramp and have a change in its angular velocity. So let's go ahead and write that down. So my answer would be force of friction. Okay, and now directly below that, it says briefly explain your reasoning. And if it's asking me to be brief, I'm going to be extremely brief. Now, you may be compelled to write a paragraph-length response or add fluff to your answer, but try your best to be as direct and to the point as possible. And I'm going to do this in just a sentence. So let me explain it briefly. I would say the force of friction causes a net torque to be applied to the center of mass of the wheel, which causes it to rotate and change its angular velocity. And if you can see, just in 15 seconds, I was able to write a very succinct and to the point answer that not only gets me the points, but clearly saves me time. So you want to be as direct and as simplified of a response that you can answer with, okay? All right, so now let's move on to part B. Okay. For part B, it says, for this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of force of static friction exerted on the wheel is 40% of the magnitude of force or force component directed opposite to the force of friction. Derive an expression for linear acceleration of the wheel center of mass in terms of m, theta, and physical constants as appropriate. So that's the fourth rule I was talking about, right? So they give us kind of like hints here. In this expression, we can only include mass and theta and physical constants, whatever that may be. We'll have to find out what that is. But yeah, so they're kind of giving us a hint of to what we can use, and we're clearly finding linear acceleration. So in this little paragraph of a question, all they're asking is you just have to derive an expression for linear acceleration, and they give us information about forces. So right now I'm thinking of the physics principle of dynamic forces. In order to do anything with forces, what is the first step we should take? Yeah, we should actually draw a free body diagram. So let's go ahead and redraw a free body diagram, this time representing the wheel with the dot. And I'm just going to draw the force of normal, force of gravity straight down, the force of static friction, and obviously I would go ahead and break this up into components because we're not in the answer space anymore. Okay, so that is my FG in the x direction, and that is my FG in the y direction. Remember, theta goes right between FG and FG in the y direction. All right, so now we know that the wheel moves along this x-axis right here. So right here, it moves down that ramp like that. So before I would even use any sort of equation, I'm going to go ahead and write a net force equation. Remember, the net force in the x direction is equal to the mass of the wheel multiplied by its linear acceleration. And we know that if we want to find acceleration, we have to do f of x divided by m, which is equal to a, right? But this is not its most simplified form, obviously, because we don't know what f in the x direction is. Like, we can go ahead and definitely substitute things in for that and make it more simplified. So let's go ahead and do that. So we know that net force in the x direction is equal to FGX minus force of static friction, which is equal to MA, right? And we can automatically put in mg sine theta, right? Because this would be mg cosine theta, and this would be mg sine theta. So we're going to put in mg sine theta minus force of static friction is equal to ma. Now, if you did not read this question carefully enough, you might have assumed that force of static friction is equal to some coefficient of static friction times force of normal. However, do they ever talk about coefficient of static friction? No, right? So we automatically know that we're not going to have anything, the equation won't have anything to do with that. So let's go ahead and read that question one more time. It says the magnitude of the force of static friction exerted on the wheel is 40% of, so it's 0.4 times the magnitude of force directed opposite to the force of friction. So what is directed opposite to the force of friction? Well, that's FGX. So force of static friction is equal to 40% of times FGX. So we can rewrite that and say force of static friction is 0.4 mg sine theta. So let's go ahead and substitute that in the equation is equal to, minus 0.4 mg sine theta is equal to ma. And conveniently enough, these are like terms, so you can go ahead and combine them, and you get 0.6 mg sine theta is equal to ma. And remember, we're solving for linear acceleration, so we're going to go ahead and divide mass so that this cancels out. And I'm going to simplify completely. So if I can cancel out the masses, I'm going to go ahead and cancel out the masses. So this gives us 0.6 g sine theta is equal to acceleration. And that is our final answer for part B. All right? So now let's move on to part C. In the second experiment, on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest from the same height. The block slides down the ramp with negligible friction. Which object, if either, reaches the bottom of the ramp with the greatest speed? So now we're comparing a block. Now we're comparing a block with a wheel. So here we have the wheel. Here we have the block of ice. Both have mass m, so we know that mass probably doesn't have a really big factor in it because they weigh the same. So which one would reach down with the greatest speed? All right. So we know that the wheel has a force of static friction, as mentioned in the question, and also as mentioned in the question, the block of ice has no friction. So if this has no if the block of ice has no retarding or counteractive force, it means it should reach the bottom with the greatest speed. So I would say that the block of ice would reach down with the greatest speed, right? So I would check this space right here. And now it says briefly explain your answer in terms of forces. And like I mentioned earlier, I kind of reasoned this out. Ice would reach first because there is no retarding slash counteractive force that resists its motion, right? Okay, so now that makes sense. Again, super brief, super short, absolutely to the point, saves me a ton of time. Next, it says briefly explain your answer, now reasoning in terms of energy. So instead of using force, now we're going to use energy to explain it. Okay, so what is the difference between, let me draw this diagram again. What is the difference between a wheel and ice, or a block, any block actually? So a wheel actually, it rotates, right? And a block only has translational motion. And actually, let me go back to the wheel. The wheel not only rotates, but it also has translational motion, correct? Because it spins and it also moves down the ramp, whereas the block of ice simply just moves down the ramp. So if the wheel has both rotational motion and translational motion, that means some of the velocity goes into angular velocity, right, in order to rotate it. And then you only have a little bit of linear velocity. However, there's for the block of ice, there's all of the initial energy goes into linear velocity. So therefore, you have a much higher linear velocity than the wheel. So let's go ahead and put those into words in as few words as possible. Okay, so I'm going to start with both objects begin with same potential energy. Okay, so that's one sentence. A block of ice has only translational motion / translational kinetic energy. Therefore, all of the initial potential energy gets converted into kinetic energy, giving it a higher linear velocity. Okay, and yeah, that's it. We did it in 2 sentences, and it's directly to the point, and I think it conveys the message across. So yeah, that's how you would approach an AP Physics 1 FRQ. And in the next video, we're probably going to go over another example. Good job, guys.